All right, let's try to. Yeah. So what is the first combinatorial Noshtolen-Satz theorem? Yeah.
Yes.
We'll call it Theorem 1 of Combi-Noshtolen-Satz.
First theorem.
By the way, I should all mention this is like the work of Alon Noga. What's his name? Alon Noga. Or Noga Alon.
No.
I think he's from like maybe Israel or something. I don't know, but like.
Surely he's German.
But yeah, but this is pretty cool. I mean, like we're just basically reading his paper, and so you're seeing sort of this guy in action. I'm gonna see how clever some people can be, and then
I think if he disabled the waiting room for Zoom,
yeah,
it would be better. Because last time I got in there like waiting, and I was like, I wasn't bothered.
Just leave.
Yeah.
Oh, okay.
So now people just join in instantly.
I just wish it stays disabled though, because every time it just enables itself. I don't know how to keep it off.
I don't think there's a way. They put it there just in case for people who like for the other case.
Yeah. Yeah, and I think the other time I kind of remember when like it was kind of it came out of like a snippet of a research paper was like lifting the exponent.
Oh.
So it was just kind of. But like I think this one is much more advanced than lifting the exponent. Okay, so the first theorem, what is it? So you have these.
Yeah.
So you have these SIs, right?
Yes.
These sets. So and you define the polynomial GI. Okay.
Yes.
So we're always working inside of n variables, yeah. We have, yeah.
The house is getting rented.
So GI equals. So GI is a polynomial in n variables as well, but we only really have one variable in there. So it's the product of x minus s. As s ranges from si, and si is like a bunch of sets.
SI. Oh, hang on. Let me. SI. Wait.
Like is GI like a one variable for?
Oh yeah, so it's inside of f.
Oh.
It's inside of the, but it only has one variable in it.
What they make.
Wait, what would you like? Only has one.
So
it only has xi in it.
So it creates a polynomial for each.
Like if it was just like x and y, g of x only has x in it. And gy has only y in it.
So it's like a polynomial for only one variable.
Oh wait. For s.
Examine small cases.
Wait. Xi is a variable. And
Yeah.
S is the stuff that's in the set.
Yeah. Okay. So I goes from 1 to n. Yeah.
Okay. Yes.
Yeah. See, like this kind of stuff, I feel like there's some theory which is kind of really good substitute for problem solving because it's about as hard to understand the theory as it is to solve a problem.
Yeah.
You know what I mean?
This is also.
Yeah.
Yeah.
It's almost like I feel it reminds me of those guys that are sign languaging for some. It's like I'm writing here and he's just like signing. But have you ever seen those sign language people? Like they're like they're always like, the guys like, saying some real serious stuff and they're just like.
They have like.
You know, like it's like what?
Yeah, so they have a really professional.
Sign language and comedy.
Huh?
Sign language.
Yeah.
This man is literally making
What?
He's putting cookies in the cereal.
Oh,
wait, isn't that
you have like a spoon? Okay, good.
Yeah.
Yeah, and then he just. I'm like, oh god. It's really all about the cleanup cost. Okay, so we have these G's, right?
Yes.
Under what conditions? So f is 0 on a whole bunch of stuff. F.
What are we trying to prove?
So maybe I write the conclusion.
Yeah.
So something about f, yeah.
Yeah.
F satisfies.
What's F?
Oh wait, this is the thing with like degree, I think. some sort of degree.
Oh, so I think F satisfies. No, we already had degree, I think. Yeah, okay, but it has something. Yeah, you're right. The F has a degree of F is equal to the sum of the TIs.
Yeah.
TIs, yeah.
Yeah.
Okay, so there is one maximum thing.
So F is like the maximal thing.
So there is a like.
Yeah. Yeah, exactly. Because F is. What is it? So F
is like the big daddy polynomial. You make sub-polynomials from GIs.
Yeah. And then one of the terms there's a term x1 to the t1, x2 t2.
Yeah.
That exists.
Yeah, that exists. Yeah.
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 So that's one way to realize the degree.
Wait, aren't those two equivalent?
Not quite, because the degree could be summed up. Like the sum could be mismatched.
Wait, what?
Like you could have x1.
Oh,
This is what we were trying to
The
do.
t's are not the degrees.
I
Yeah.
remember. This is what we were trying to do here.
The t's aren't the degrees of the variables.
Wait, what are the
The t's, I guess they just have to be things which are less than, I think, ti. We can check this, less than si.
Oh yeah. I remember this.
Wait, so it's like the other thing, but like weirder.
Yeah. So
Before
the
the
other
TI.
thing, the ti was the degree of the xi. Yeah.
Yeah.
Here the ti is
not.
sort of the degree, but it doesn't have to be, because you can have another.
So you can have like another you can have
x1
another
to a
term.
huge power. Yeah.
Yeah, with the like big stuff, but then okay.
Yeah, but it has to have this mixed one, like
It has
that.
this random. Okay.
Yeah. Okay.
Waiting for the combi.
Oh, actually, maybe I'm getting some assumptions confused. Maybe. Oh, actually, I don't know if this part might be for the next theorem. Okay, just keep this in mind, yeah? So what's the conclusion here? The conclusion is that F is equal to a sum of HI/GIs.
Oh, I think I remember this now. Wow.
I'm trying to figure out the assumption for it. Actually, I think this assumption might be for the next one.
Oh, wait, just saying GI has degree SI, right?
Yeah.
Okay.
So it doesn't quite make sense, huh? So I think F should just be 0 on all the S's, yeah?
Wait.
So clearly, like.
Is that condition or?
Yeah, that should be a condition.
And what's HI?
Oh, so HI is just some polynomials. Yeah, so we spent quite a bit of time in the last lesson explaining why this thing is called combinatorial non-Stahlensatz, and it's got to do with the form of the conclusion. So the normal non-Stahlensatz is like f to the power of k equals HI/GI summed, but you don't know what the GI are.
Oh.
But here it's like you know what the GI are. It's given in the condition. And you don't know what the HI are, but you know that the degree of the HI is at most the degree of F minus G. Yeah?
GI is just SI.
Yeah. I'm pretty sure now this is not in this one.
Okay.
We can check it in the proof.
Oh. But,
yes, ever the proof.
So you have a G of I defined like that on the on one of the variables, and
Yeah. So can you see that, like, so if you sub into GI, anything whose ith component is in SI,
so D is it.
it'll get 0, right? So it's like it could be anything, and then in the ith entry it's SI, yeah?
Yeah.
And then it's 0.
Yeah.
Yeah. So if you look at all the G's at once, right? The things which are common zeros to all of them are the ones that are like S1, S2, up to Sn, right?
where so like like when every term is in one of the things.
Yeah, so for example, like if you have like G1, right?
Yeah.
The thing that makes G1 0 is really S1, right? And these could be like W, Z, it could be anything, right? It'd be 0, yeah? And for G2, it's just S2 here, right?
Like S2 being like an element from S2.
Yeah, and here, right? And then the others can be anything, yeah?
Yeah. So when you have one like a term in each one that being an element from its set,
Yeah,
that sends it to 0, then
yeah. So then the common zeros of all the G's, right,
it's just those.
are the things of the form like S1, S2, yeah? Like Sn, right? So saying that F is 0 on those things is saying that F, the common zeros of G are also zeros of F, right?
Common zeros of G.
Yeah, because the zeros, the 0 of G, like the common zeros of G are exactly the things in the product of S,
Yeah.
these
Yeah,
S tuples.
that's F.
Yeah,
Yep.
and so the common zeros of G are
The
zeros of F.
yeah.
Yeah. So that's like a big part of the Stellensatz that we're trying to explain.
Where the zeros are.
Yeah, so in the Stellensatz is basically saying like you can think of like geometry as like subsets of the plane or whatever space. So in this case, it's n-dimensional space because n variables, and you can think of them as sort of the zeros of polynomials. Sets of zeros of polynomial things, and so there's a correspondence between these subsets and polynomials, and that's how you get that formula. But we skip it today because we want to. Motivation. It's on the video somewhere, you can look it up. Okay, so the motivation is only for the name. Like the proof is independent. So okay, so let's see how this proof works, right? You take a GI, yeah? It's equal to the product. Do you remember this, guys?
Kind of.
Could you tell me what to do?
Hold on. It's equal to the product of x minus s I. Or just s, I guess.
Yeah.
Yeah. Right.
So it's a monic, right?
Yeah. Also, we can use.
So
Recurrent.
you can expand it xi, and then you can just call this ti plus 1, yeah? That's the definition of ti. So define ti to be the degree of gi minus 1, yeah? So then when you expand it, right, you get it's monic. The first leading, like the highest degree term will just be that, right? And then we say it's like minus a whole bunch of stuff, yeah?
5 minutes ago, Ti was the degree.
Yeah, now it's the degree of something.
Abusive notation.
Oh no, but it was the degree of f.
Yeah.
Now it's the degree of g. So this actually achieves the degree of f being ti. That's why it's plus 1.
Oh.
Okay. Yeah. So it's minus some lower order terms, right? So call it like g I j. Yeah.
Oh my
Yeah.
lord, what is this?
Yeah. The elementary symmetric polynomials. Gij. Yeah. Okay. So what's cool about this is when you substitute. Okay, so you do this for all the GIs, right? And then you look back at F, yeah? Okay, so F, if we want to use the lemma, right? We need the degree of F to be the right size, yeah? Okay, but at the moment, we don't even know anything about the degree of F.
Yeah.
It's arbitrary F, basically, right? So how can we say the degree is low if we don't know anything about F, right? Well, the thing is, we're allowed to decrease the degree because we don't want to conclude f is 0, right?
Yeah.
We only want to conclude f is equal to a sum of hg's, right?
Yeah.
So we're allowed to minus hg's from f and then conclude it's 0.
Oh.
Then you can conclude that f is equal to a sum of hg's, right? Yeah. So you can minus hg's, and if that hopefully we can lower the degree with it.
Oh.
Yeah. So look at how you how you lower the degree with hg. So basically, imagine imagine subbing in something like you take GI, right? And you sub in something something in SI, yeah? Yeah, it's equal to 0, right?
Yeah.
So what that means is it means that when you sub in the SI TI plus 1, right, is equal to a sum of GIJ SIJ, yeah?
Oh yeah.
That makes sense? Because this is 0.
Yeah.
We submit something from
Yeah.
SI, and then yes,
Right? So what that relation is telling you, right, is telling you that like SI to a high power is equal to a bunch of SIs to a lower power.
Times some coefficients.
Yeah. So so you can do the corresponding operation in F, right? So if F has like a term that's like xi to the power of ti plus 2, right?
Yeah.
Times like
Times
a bunch of stuff,
Yeah.
xj, you can rewrite that, yeah, as xj times xi, right? Times
that thing.
basically that thing, right? So
that thing.
sigma gij xij.
For xi being an element
Xi
of
equals some SI.
Oh no, so we can see it can do it with SI, right? Now we actually do it.
Oh, it's like J.
So we actually do it we do it for variables now. Yeah.
Oh wait, how is that?
So when it's not F anymore. So this is now, I guess this turns into like maybe what we call F bar or something. Yeah.
Alright.
That makes sense.
Yeah, so we transform.
So we take F, right, and we apply this operation to the variable, not to the substituted thing. Yeah.
And so we
And then we call the thing that you get F bar. Yeah. Okay. So if you actually know what this operation is, it's actually minusing from the operation is actually just corresponding to F minus like HI/GI, if you think about it.
Perhaps.
Yeah. Because the old thing here was just xi to the ti plus 1, right? So you minus that dies, right?
Whole thing is xi.
And then the minus,
Oh,
that bit becomes plus, yeah?
yeah. And
So-
then your hi is just your xj, xi, and this.
Yeah, exactly. Okay. So notice the degree here, the hi has to be less than the degree of f minus g, right?
Degree is less.
So we need to check the condition. The degree of hi is always less than or equal to the degree of f minus the degree of g. Yeah.
And that seems true.
by logic.
Well, yeah, because hi is just this part, right?
Yeah.
Yeah.
Doesn't seem to
And the degree of
F is bigger than.
and the degree of f is bigger than or equal to the degree of the whole term, right? Yeah. So the degree of hi plus the degree of g
can be outwards.
is less than or equal to the degree of f, right?
Yeah.
So then you just put it on the other side.
Just yeet it. Okay.
Okay. All right, so we good?
Yeah, I would not be able to replicate this.
Well, we are just getting it from the source. Like this is straight from the mouth of Elon. And yeah, I mean, and usually people, if it gets to this kind of status, it usually has some impact. And having impact normally equates to not being able to think of it themselves. Okay, so we good?
Yeah.
So can you see what happens? So we did these operations on F, right?
Yeah.
Which amount to subtracting HIGIs from F, yeah?
Yeah.
And so, but every time you do it, it decreases the degree, yeah? See, the degree is now less, yeah?
Yep.
Because that was TI plus 1, now it's less than TI plus 1. Yeah, and then you just do it again.
When you're allowed to do it again.
Yeah, because you're just minusing each time, yeah?
Yeah, like what are you minusing this?
Oh, okay. If you do it again, right?
Yeah.
I guess you'd be minusing like another
And GIJK.
another GI, right?
Okay, wait, but
But now you're timesing by another. It's slightly different HI. So you're just timesing by XJ this time. Yeah. Oh yeah. It's a G.
What is this? Oh, just this
it
draw.
depends on your J.
Yeah. If the J was too small enough, you don't have to worry about, right?
Oh, wait,
So if
it
J
must
was
show you
just
someone
like,
sent it.
so the J has to be like TI for it to be big
This
enough to even
guy,
worry about.
yeah.
Yeah. And then
So and then after you keep subtracting, you're just left with a bunch of stuff with less degree, less than like G.
yeah. So the degree is TI. That's the point, right?
Oh,
Because the relation will always kill things if TI plus one or more. Yeah. So F bar has the property that, so F bar is both F minus, so F bar is equal to F minus a sum of HIGIs, yeah, and it has the property that it has degree TI on all the variables or less,
yeah,
or less, right? And you sub it gets 0 when you sub everything in, right? Because both G and F are 0 when you sub them in. So if you sub S's into F, right? F bar, yeah? That's the same as just subbing S's into the F, but applying these relations, right?
Yeah.
And because the relations are true, because the G's being 0, right? So what that means is when you sub in those S's into F bar, it's also 0.
and wait, hang on, why is it? Why is it 0 when you sub it to F?
Oh, that was the assumption. That was the assumption. This
It's also a
condition.
class of GI, so if you something to F bar.
Oh, so F, because when you went up and it was like F is like arbitrary thing of that was like,
Oh,
okay, so
oh
it
yeah.
still has some relation to the S.
Yeah, yeah.
Okay.
Yeah, yeah.
Completely arbitrary.
Yeah, yeah, yeah. If it's completely arbitrary, it couldn't, because the final conclusion, right? It has to be 0 on all the S's, right? So the assumption has to
Oh,
include
yeah,
that.
and so then you go back up, and then so like because when you sub in, like it's when you sub in those values, it is true that F bar is equal to F, or it's equal to
Yeah,
F, and
So-
that's equal to 0.
yeah. Like another way to look at it is if you sub in the values, like the S's, right? HIGIs are all definitely 0, right?
HI.
Because the GIs are
Yeah.
0. So the HI is going to times 0.
Yep.
And then the F's are by 0 by assumption, right?
So one.
So then F bar has to be 0 because it's the difference of
Yeah.
zeros.
Then now you have that.
Now you have the lemma, right?
Now wait, now you have that thing down the blue thing. Then you do the blue thing.
This blue thing.
Yes.
Yeah, so now you have this, right? And it satisfies the lemma,
That is why the number.
which says if the degrees are lower than the sizes of the sets, then it's a 0 polynomial.
Oh.
Yeah.
Oh, that's where that comes. That's where that.
Yeah. So
Yeah,
now it's a
that's
0
right.
polynomial, right? And so that means F is a sum.
yeah, this is good to that.
Yeah.
Oh.
Yeah. Don't go to second hand. Go straight from the source. Alon. Noga Alon.
Oh, this is so nice.
Yeah.
Who's supposed to come? She doesn't seem to be coming.
Yeah. So that's proved. Is any questions? Actually, there was a little slight sub statement, but I don't know if I it's also that I think it was like if something about what was the statement? So the theorem itself says F vanishes over all. Yeah, F is 0 for all the SIs. Then yeah, so there's an extra little like moreover if you're interested. So if the F's and the G's actually lie in a sub ring, so if so the coefficients of the polynomials of F and G, right? If they actually all come from a subring of the field, so for example, they're all integers, Okay. Then the conclusion is the HI also have integer coefficients.
Oh,
Does that make sense?
oh yeah, fair enough.
So,
Yeah.
So
or
kind
like
of
or like
complex.
if they're real, if everything's a real polynomial, but these G's and F's are like rational coefficients, then the H also rational
yeah.
coefficient.
Okay, it kind of reminds me of the I think Gauss's normal. So it's like if
Oh
it's
yeah.
reducible over like if a rational polynomial is reducible over
Oh yeah.
irreducible over something like that.
Yeah. So then and this is actually quite obvious in this situation, okay? Because if you look at how we define the H's, right?
Yeah.
The H's just come straight out of the F's.
The like coefficient anyways.
Yeah. Like, you're not square rooting them for no reason and stuff, yeah?
I forgot the definition of ring.
So ring is it's basically it's got multiplication, addition and subtraction, and the field also has division.
Oh.
It's pretty much. Actually, yeah, I don't know why. Like, I bet you this stuff can be actually taught in like primary school. It's just that like,
They want to like grasp this.
well, it just depends on your reaction when you learn it. If you thought it was a really hard idea, you're never gonna try to teach it to young people. You know? But if you realize there's no content, it's just a definition, right?
Yeah, definition.
You can teach it to anyone. Alright, I'm gonna have to chase up this